This video is the second part for the topic of how to verify solutions to differential equations. We're going to have some tricky problems here. Example 1. In this case, the proposed function is given implicitly. Namely, if you check out this equation, you cannot write your y in terms of x explicitly. So that means we cannot use the standard way to get the derivatives of y and then plug them into the equation. Nevertheless, we still need to find the derivative in order to verify. So we have to use something so-called the implicit differentiation to find the derivative. This is something we did in calculus 1. And the approach is you simply take the derivative of the whole equation with respect to the argument x here. For the first term, it's pretty easy. It's just 1. For the second term, because the derivative is not with respect to y, but to x. So here, actually, we have a composition of two functions. We know the chain rule is going to be applied to that case. And these two functions, you can tell one of them is going to be the square function. Another one is just the y, which is something we don't know, but we know it's a function. That's why we say it's a composition of two functions. Similarly, for the last term, you're going to say a composition of exponential function, and you have here xy, which is a function of x. So again, you can use the chain rule in this case, and we get the derivative of the exponential function is going to be itself, and then you're going to do the exponents, this part's derivative, with respect to x. So now we just need to figure out these two parts. So for the second term, you understand the derivative of a y squared with respect to y is going to be 2y. And for the dy dx, we don't know what's this. It's actually something we're looking for. So we just write it as y prime. And for the last term, in order to find the derivative of x, y, it's actually a product of x and a function of x. So we have to use the product rule. Namely, you have to do the derivative of x, which is going to be 1, and then times the second factor y. And then plus x times the derivative of the second factor, and you get y prime. So by this means, we can get the y prime in the equation. And you can just use algebra to isolate your y prime. Namely, we first of all combine the y prime terms. You're going to get 2y, this many, and x times e to the xy, this many. So totally you're going to get 2y plus x times e to the xy, this many y prime. And for the other terms, you also combine them. You get 1 plus y times e to the xy. And then you move these two terms to the other side. You get -1 minus y times e to the xy. Divide by the coefficient 2y plus x, and then e to the xy. That will be the expression for the y prime. And now we can plug this into the differential equation. So as you can tell, when we plug the expression in, we notice that there's a cancellation in this fraction, because this factor, which is in the numerator, is the same as the denominator. After we cancel the denominator, we're going to get the first term will give us -1 minus y times e to the xy. And then you copy the second part, which is 1 plus y times e to the xy. And apparently you see the cancellations, and you get 0, which is the right-hand side. So we just confirmed the two sides, they match. Therefore, the implicitly defined function from this equation is going to solve the differential equation. Example 2. This one is similar to example 1. We once again get some function y implicitly defined from this equation. And we want to check whether or not this is going to solve the differential equation. So we'll use the same approach. We do the implicit differentiation. So first of all, we're going to take the derivative of this equation with respect to x. And for the left-hand side, actually, this one is the composition of not only two functions, but three functions in this case. And the three functions are, first of all, you'll see the innermost level is going to be just the y, which is a function we don't know, okay? To put it into the format of the chain rule of three functions, this is the chain rule for three functions. I'm going to denote the y as h here. Okay. And then the the next level of the composition is going to be sine. And then the outermost level is going to be the square. So we got a composition of actually three functions. But for the chain rule of three levels of composition, you can say the formula is kind of similar to the composition of two functions, right? So you simply get the derivative of each level, okay? And then you're going to say the derivative of f with respect to g is going to be 2g, right? But g, we understand, is going to be sine, so that's why you're going to get twice of a sine y. And for the middle level, the dg, dh, in this case, is pretty much the derivative of sine. That will be cosine. Finally, the innermost level, you're going to get dh, dx, which is dy dx. So that will be the derivative of the left-hand side. The right-hand side is straightforward. We know this is the power, so its derivative is going to be simply 8x. Now, we get an expression with the dy dx, which is something we're looking for. So we simply divide both sides by the coefficient, and then we cancel the 2. We're going to get the y prime is going to be 4x over sine y cosine y. Now we can plug the y prime into the equation. And apparently you can see the cancellation. So the sine y cosine y get canceled. And you're going to get 2x times 4x, which is going to be 8x squared. And then minus the second term of 4x squared. That will be 4x squared. And we know from the given equation, 4x squared is nothing but sine y squared. So you're going to say this is going to be sine y squared, which is right-hand side of the equation. So we just confirmed, once again, the two sides, they match. Therefore, the function implicitly defined is going to be a solution to the equation. Example 3. This problem is a little different from the first two. Here, we were told that the given function, which is y is equal to x to the r times natural log of x, it is going to be a solution to this equation. We don't have to verify it. But something we don't know is there's a R, which is a constant. So how to solve this problem? It turns out the idea is going to be the same. You simply plug this into the equation, and then you're going to get a constraint of the R. And then from the constraint, which actually is going to be an equation, you can solve it and get the R value. So we first of all find the derivative of the function y, because this is a product of a power and a natural log. So we first of all use the power rule. We do the derivative of the first factor times the second factor plus the first factor times the derivative of the second factor. You use the power rule for the first derivative. You use the derivative for natural log. You're going to get that will be x to the -1. So simplify, you're going to get your y prime is going to be r times of x to the r-1 times natural log of x, and then plus x to the r-1. And now we need to do another derivative to find y prime. And you notice that we have a product here, which requires an application of the product rule. And then we have a power, which requires an application of the power rule. So we simply apply the rules, and we simplify. We'll get the y double prime is going to be r times r-1 times of x to the r-2, and then times natural log of x, plus 2r-1, this many x to the r-2. And now we can plug the y and its derivatives into the equation. So this time we don't check the two sides. We make the two sides equal because we already know it's going to be a solution. So you will say for the first term, we can factor x to the r-2 out. And for the second term, we can factor the x to the r-1 out. And then you will say the x squared times the x to the r-2 will give you x to the rth. Similarly here, x times x to the r-1 will give you x to the r's. And the last term, it also has x to the r's. So we know x to the r's is a common factor. And then we put all the other coefficients in the bracket here, and then we try to simplify it. In this case, because x is going to be greater than 0, that's the domain for this function. Therefore, we know x to the r's for sure is not going to be 0. And we can divide this equation by something which is not equal to 0 to simplify it. So we're going to get the coefficient here has to be 0. In this coefficient, we have essentially two different things. One is the natural log. The other one is a constant. So we just combine them. We put all the natural logs together. We get this many. You get r squared minus r minus another r, that's minus 2r. And then plus 1. You have this many natural log. And for the constants, you simply get 2r minus 1 is going to be minus 2. And in order to make this equal to 0, we understand the coefficients for the natural log has to be 0. And also, this constant has to be also 0, because this is true for whatever x. So that will force us to get r squared minus 2r plus 1 is equal to 0. That's a coefficient for the natural log. And 2r minus 2 is equal to 0 as well. And from these two equations, actually, you're going to get the same solution. namely r is equal to 1. So we get the conclusion. In order to get a solution of this format, your r has to be 1. Example 4. This example is similar to example 3, but it's going to be a little bit more difficult because you're going to have 2 constants involved. So you have to specify both the alpha and the beta. You can see the alpha here is argument for the cosine part of the argument, and the beta is the coefficient for this exponential part. Well, just like what we did in example 3, we're going to simply plug this into the equation and force the 2 sides equal. So we have to first of all find the derivative of this function. And we notice that we have the first term is a product of an exponential term and a trig function, which requires the product rule. You can see the derivative of the first factor times the second factor, and then plus the first factor times the derivative of the second factor. And then for the second derivative, you simply do the derivative for this exponential term. Well, when we figure out the 3 derivatives here, the first one is straightforward. But the second and the third one, these 2 derivatives requires applications of the chain rule. So for the second one in particular, we're going to have this is a composition of cosine and a polynomial alpha x. We understand the derivative of cosine is going to be sine, and the derivative for the inner part will give you an alpha. For the last term, it's a composition of the exponential function and a polynomial 2x. So the derivative of the e part is going to be itself. And the derivative of the inner part, 2x, is going to give you a 2. So that's our y prime. And then for y double prime, you're going to just take derivative every term here. We're going to say the first term and second term, they are products. So we have to apply the products rule. And you just need to figure out all the derivatives here. For the first one and the third one, it's straightforward. But for the second, the fourth, and the fifth derivatives here, we have to use the chain rule again. Well, because we have been doing this, so we know the formula is going to be the following. So namely, for the second part, you can say the cosine's derivative is going to be negative sine. And the inner part, alpha x, will give you an alpha here. And for the fourth term, the derivative of sine is going to be cosine. And the inner part will give you an alpha. And for the last one, the derivative of exponential part is going to be itself. And the derivative of the inner part is going to give you extra 2, which will give you a 4. Okay, now for this expression, we're going to have 3 different types of functions. Namely, we have e and then times cosine. We have e and then times sine. And then we have e to the 2x. So we can combine the like terms. Now we can plug the y and its derivatives into the equation. And once again, we have a lot of like terms here, which can be combined. So once again, get e times cosine, e times sine, and then e to the 2x. So we combine the like terms. And we can simplify. We'll end with the left-hand side is going to be 1 minus alpha squared, and then times e to the x times cosine r of x. And for the e to the x times the sine r of x, this part is canceled. And then we have twice of beta times e to the 2x. So that's our left-hand side. In the right-hand side, that's always 6 times of e to the 2x. And we know this is an identity. So that means you're supposed to get the same number of e to the x times cosine r of x. We have 1 minus r squared, this many in the left-hand side. But we don't have any in the right-hand side. That means you have 0. And to make them equal, that will require the 1 minus alpha squared is going to be 0. Similarly, for e to the 2x, you have to have the same amount in the two sides. That requires the 2 beta is equal to 6. So comparing the coefficients of the terms here, okay, we're going to get 1 minus alpha squared is going to be 0, which implies the alpha is going to be either plus or minus 1. And 2 beta is equal to 6, which implies your beta is going to be 3. So that means in order to get a solution of this format to this differential equation, we must have the alpha is either positive 1 or negative 1. And the beta has to be 3. That's all for this video. And thank you.